Hi students, Professor Nugent here. We just introduced the random effects model and we discussed that random effects is consistent and asymptotically normal as the sample size gets large with the number of time periods fixed under a certain set of assumptions. Let's discuss those assumptions. First, for each I, the true model is the true population model is given by the following. YIT is equal to, let's include beta naught plus beta 1 x1 it through beta k xkit plus ai plus uit for t equals 1 through t, where the beta j are the parameters to be estimated, ai is the unobserved effect. Here I've included the intercept because we later include the intercept in our transformed equation, so it's useful to start with that in our true model. And our interpretation of this model is the same as with fixed effects. The model is linear in parameters, and the effects or the parameters are constant over time. The unobserved heterogeneity, the unobserved effect, is constant over time. Second, we have a random sample from the cross-section. And that is the same as with fixed effects, random sample from the cross-section. Third, we have no perfect relationships among the xj, so there's no perfect multicollinearity. And we're going to add something to the third assumption. The cost of allowing time constant regressors is that we must add assumptions about how the unobserved effect how AI is related to the explanatory variables, the xj. And we have made that assumption. We started with that, that the covariance, we stated that the covariance between, or we say the covariance between xj it and ai is 0 for t equals 1 through t, j equals 1 through k. All right. Now let's get to our fourth assumption. for each time period t, the expected value of the idiosyncratic error UIT given the explanatory variables in all time periods and the unobserved effect, so xi and ai, is 0. This is the same as with fixed effects. So we have strict exogeneity, and we're going to add an additional assumption that the expected value of ai given xi is a constant. It's constant. Beta naught. So the expected value of ai given all explanatory variables is constant. So assumptions 3 and 4 are modified from the fixed effects assumptions. And in assumption 4, the expected value of ai given xi equals beta naught rules out correlation between the unobserved effect and the explanatory variables. And this is the key distinction. So this is the key distinction. This implies this, and this is the key distinction between fixed effects and random effects. Under these 4 assumptions, random effects is consistent and asymptotically normally distributed. We have a 5th assumption. So let's write that down. Random effects is consistent and distributed asymptotically normal. Now, the 5th assumption, the conditional variance UIT given xi ai is equal to the unconditional variance UIT, which is equal to sigma squared u for all t. So homoscedasticity, and we have to modify this one. The variance of ai given all explanatory variables, also constant. So we have homoscedasticity in the errors. And 6, for t not equal to s, the idiosyncratic errors are uncorrelated. So the covariance between UIT and UIS given xi ai, that's equal to 0. So the 5th and 6th assumptions get us exact t and f distributions, and under the 6 assumptions, random effects is much more efficient than fixed effects. Sometimes you will hear the random effects estimator referred to as the efficient estimator. However, we don't rely on fixed effects for efficiency. We rely on fixed effects for robustness to the correlation between AI and xjit, which is why you will sometimes hear fixed effects referred to as the consistent estimator. Just a couple more nuances around random effects, and we will discuss those nuances around random effects in the next video. Stay tuned.